Welcome to this video. In this video we will be talking about errors and tolerances in solution and function, so that by the end of this video you will be able to calculate the tolerances in solution and function, and you will be able to choose between using either the tolerance in solution or the tolerance in function, and you should be able to calculate the true relative and the estimated relative errors. So errors and tolerances. So let's do a couple of definitions. First, let's write the true solution as x sub ts, ts for the true solution. So if xts is the true solution, then f of xts has to be equal to 0 because we're looking for the true solution that is a root to f of x equal to 0. Now let's write our numerical solution as x sub ns, ns for numerical solution. Now, if I plug in the numerical solution into my function f, I will not necessarily get 0, because if I would get 0, then my numerical solution would be my true solution. I will instead get a non-zero value, and hopefully that non-zero value epsilon, however, is small, so that I'm almost solving f of x equal to 0. So let's recap some definitions. First off, the true error for nonlinear equations is still the true solution minus the numerical solution, but we need the true solution to calculate this. The next quantity I want to look at is the tolerance in solution. So what's this? That's the maximum difference between the true solution and the numerical solution. So here's an example from a bracketing method. In a bracketing method, I know that the true solution is somewhere in this interval, in this red line. So if I set my numerical solution equal to the midpoint of this interval, right, which is a plus b divided by 2, if I set that as my numerical solution, I know that my true solution is somewhere between my numerical solution plus or minus the tolerance in solution. And the tolerance in solution then just simply becomes half the size of the interval. So b minus a divided by 2 absolute, because the tolerance in solution is a positive value. Couple of comments. So basically, the tolerance in solution is an error band, right? I have a true solution that will be in the interval given by the numerical solution plus or minus the value of the tolerance in solution. The other comment is that unfortunately, the tolerance in solution can be calculated easily only by bracketing methods. But for bracketing methods, it's pretty straightforward and easy. The tolerance in solution is just half the size of the current bracket. But we won't be able to calculate the tolerance in solution for open methods. Okay. Next up is the tolerance in function. And for the tolerance in function, we are going to ask how far is f of my numerical solution away from f of my true solution, which is 0. So how well do I solve f of x equal to 0 if I plug in my numerical solution? Well, let's calculate this. What is the absolute value of the difference of f of my true solution minus f of my numerical solution? Well, f of my true solution, if the true solution is a root, that is equal to 0. And well, my numerical solution, well, I got some numerical solution calculated. I can plug this into my known function f, and I can calculate what f of the numerical solution is. Now, taking the absolute of this is simply the absolute value of the numerical solution plugged back into the nonlinear function f of x. And that is the tolerance in function. So let's look at that difference between tolerance in solution and tolerance in function by looking at an example. So let's say you want to fly from Phoenix to LAX, and the distance is about 322 nautical miles. And the question is, how much fuel do you need to take on board to fly this distance from Phoenix to LAX. And let's say that this function, distance as a function of the amount of fuel, is some very complicated nonlinear function that you can't solve analytically. So you're going to use some numerical technique, and you're going to find a numerical solution, x and s, that tells you I need x and s pounds of fuel to fly the distance of 322 nautical miles. Now, the tolerance in solution tells you that the true amount of fuel that is required is somewhere within the band of your numerical solution, plus or minus the tolerance in solution. Right? And so if you want to play it safe, then you would put on board the numerical solution plus the tolerance in solution in the weight of fuel that you take on board. So that's the tolerance in solution. It relates to the solution variable x, the amount of fuel. The tolerance in function, on the other hand, asks something different. It asks, with my numerical solution pounds of fuel, I can fly to within the tolerance of function to the target distance of LAX. So the tolerance in function will tell me I can fly to LAX, the 322 nautical miles, plus or minus the tolerance in function nautical miles. So there this tolerance is on the target value of the distance and not on the amount of fuel that I would need. Okay, let's talk about the true relative error. That is similar to the definition as before. In this case here, the true relative error is the absolute value of the true solution minus the numerical solution divided by the true solution. Problem is, of course, we don't usually know the true solution. And that's why we typically use the so-called estimated relative error. So what's that? Let's assume that we will have a sequence of ever better estimates for my route. Right? Something that an open method will give us directly. So we start with some initial guess, numerical solution superscript 1 in parentheses. So this does not mean that you take the numerical solution to the power 1 or the power 2. These round parentheses just indicate that this is a value in a sequence of ever better estimates for the true solution. So we'll have this sequence. And we will calculate the estimated relative error by taking the best value that we have, so after n iterations, minus the prior iteration value, so iteration n minus 1, divided by the best value that we have available, the n iteration value. And that is actually something we can calculate, right? If we have this sequence of ever better values, we can directly calculate this estimated relative error using the last two estimates to our solution. And if you compare the definition for the estimated relative error to that of the true relative error, you'll see that if my latest, greatest numerical solution is close to the true solution, right, then the estimated relative error will be close to the true relative error itself. So here is the summary slide of all these definitions. We have the tolerance in solution, the tolerance in function. We have the same definition as before for the true error. And we have the true relative error, where unfortunately for the true error and the true relative error, we need to know the true solution. But for the estimated relative error, we just need a sequence of ever better estimates for the true solution, which are our numerical solutions. Thank you for watching.